Hello everyone, welcome to Unit 5, Lesson 4. In this lesson we're going to look at radical functions. Back in one of our earlier units we studied what a radical equation looked like. Now what we're going to do is have a look at what the graph looks like. The important thing that we're going to be looking at here is basically what is a radical function, and that's going to be something that'll have its variable inside the square root symbol. And they do have a specific look to these radical functions, which you'll see when I graph them on the calculator for you. And the other thing you're going to do on here is, we already know how to solve radical equations algebraically. You isolate the radical on one side of the equation, you square both sides, solve for the variable, and then check by substitution. Remember that when we solve these algebraically, you had to check, because what will happen is you could sometimes introduce an extraneous solution. Well, I'm going to show you in this lesson how to do this graphically, and there's two ways to do this graphically. We can set the equation equal to 0, then graph it, and then find the zeros like we did back with quadratics. Or I'm going to have you graph the left hand side of the equation in y1, the right hand side of the equation in y2, and then find some points of intersection. And it doesn't really matter which method you choose. You'll just probably choose whichever one is more comfortable for you to enter on the calculator. So our first example, what we're going to do here is graph this function, y equals the square root of 2x plus 5 plus 2, and let's determine the domain and range. So I'm just going to load up the calculator here for you, show you the process of how to enter that in, and then we'll find the domain and range. So the first thing we'll do, press your y equals button, and we'll enter in the equation. You have the root symbol, which is just above the x squared, so since it's in blue, we'll go second function x squared. Put the 2x plus 5 inside brackets, because we're taking the square root of the whole thing. So that whole expression we take the square root of, and then add 2 on the function. Now what we'll do is we'll have a look at this in our standard window. If we need to adjust it, we'll use our picture to adjust our window settings. So hit your graph key. This actually is a fairly decent size graph, so we don't even really need to adjust our window settings. Feel free to do so if you want. This is what the general shape of a radical function is. It is basically half of a quadratic turned sideways. In fact, the inverse, which I'll talk about in lesson 6, the inverse of quadratic functions are radical functions. That doesn't make much sense at this point, but you'll remember that term when I hit lesson 6, when we start to look at inverses of all the different types of functions. So you noticed a quadratic kind of opened up or down. A radical will open left or right. So in this case, what we're going to do is just look at the domain and range. Now to find the domain, you'll notice that we have some magic number in there that we have to find as our lowest point. Now the easiest way to figure out this is you have to remember that whatever's inside the radical sign has to be positive. You cannot take the square root of a negative number. The range you could probably find using your calculator, but now that I've got a picture, I'll even show you how to do that algebraically as well. So you'll see that this graph opens upward, and it basically goes to the right side of the screen. There's nothing on the left, and there's nothing down below the x-axis in this case. So I just wanted to show you the picture first. The way that I always do the domain and range with this is, since the number inside the radical sign cannot be less than 0, what I always do to find the domain is set what's inside that radical sign to be greater than or equal to 0. You cannot take the square root of a negative number. So x has to be restricted to being a positive number or 0. You can take the square root of 0. Square root 0 is 0. So solve this little inequality. Gives you 2x greater than or equal to negative 5. Divide by 2. X will be greater than or equal to negative 5 halves. And if you would have used your trace feature on the calculator, you could have approximated that as well. But here's a real quick way to do this algebraically. Take whatever's in the radical sign, set it to greater than or equal to 0, solve for x, that's your domain. So our domain will be x such that x is going to be greater than or equal to negative 5 halves, and it goes forever right of that, so x is an element of the real numbers. The range, you could see that this graph was shifted 2 units up. That's not a fluke. Notice that there's a plus 2 there. So the range of this graph would be y being greater than or equal to 2 and any real number greater than or equal to 2. So if you look at your graph on your picture, you can approximate the domain and range by using the graph, or you could actually find it algebraically. That's example 1. So you'll be asked to find domain and range. You find the domain by basically taking whatever's inside the radical sign, setting it to greater than 0, solving for x, and since the whatever you're taking the square root always has to be positive, then you'll always either have this graph either open up or down, depending on whether it's a negative 1 out front, and then you'll either be greater than or less than whatever you're adding to that radical function. So there's example number 1. Let's do a couple examples where I show you how to solve graphically. I'm not going to do any questions on solving algebraically. We've got videos on that in a previous unit. So let's just keep practicing using the calculator. Example number 2. Let's solve negative 3 square root x plus 2 plus 4 equals 1. Let's solve this one by setting to 0. So what we're going to do is set this equal to 0. Negative 3 square root x plus 2 plus 3 equals 0. And then we're going to graph that equation. Negative 3 square root x plus 4 plus 3. You'll see what happens when I have a negative sign out front. You may remember that in quadratics, that negative coefficient out front meant that it opened down. It'll happen that way with radicals as well. You'll notice that it'll be shifted 3 units up, just like how the graph at the end has a plus 3, and it'll be shifted 4 units to the left. Those same things of A, P, and Q that we talked about in quadratics actually apply to all functions. So let's put this on our calculator and have a look at what this picture looks like. And as you practice this, you'll start to learn how to picture this just from the equation. So clear the original equation. Let's enter in negative 3 second function square root. Actually, I'm going to clear my key history here. Start over again. Negative 3 second function square root x plus 2. Close the bracket. Do not forget to close your brackets in this case. Oh, it should be x plus 4. Oh, actually I made a mistake here. Let me just kind of fix this. This is actually supposed to be x plus 2. X plus 2. I'm not sure where I got that 4 from. Starting to graph a different equation. Didn't change the number inside the radical sign. So it's negative 3x plus 2 plus 3. Let's bring that screen back up again. So we'll put in x plus 2 plus 3. So there's what I'm taking the square root of, x plus 2. I'm adding 3 to it, and then I'm multiplying that whole thing by negative 3. Press your graph key, and notice the graph now opens down. Notice it's got a little bit of a more of a stretch to it because of that coefficient out front. And remember I said it was going to start 4 units up. Well, it looks like it starts 4 units up, and it's been shifted 2 units to the left. Just like our P and Q with quadratics, we still have those same variables with radicals. In fact, you'll find that when you go to 30 pure, you'll have this type of transformation, is what they call it, with all types of functions. So what we want, since we're solving, we just want to know the x-intercept. Solve means find the x-intercept. Since I can clearly see the x-intercept on my screen, I go second function, calculate, find 0, and then we just set that left and right boundary. Left of the 0, hit enter. Right of the 0, hit enter. At guess, hit enter one more time, and you find that your answer here works out to be negative 1 when x equals negative 1. Now here's the really good thing about graphing. You will not find extraneous solutions when you solve this by graphing. If you solve this algebraically, you may have an extraneous solution. Solve this with graphing, you never have to worry about it. So what I always tell students to do is, if they get good at doing these algebraically, solve them algebraically, check them with the graphing calculator. That way you get good at both skills, graphing and solving algebraically. So let's write the answer to this one. Solution is x equals negative 1. Only one answer. Let's look at another example. This one I wouldn't even ask you to solve algebraically, so this is the only one that I would do graphically. If you ever see two radical signs in the same question, this is a calculator type right off the bat. X minus 5 square root minus 2x plus 7 square root equals negative 3. This is a very difficult question to solve algebraically. You have to square a couple times to eliminate variables. You'll have binomials. It's messy. If you ever see two radicals in your question, then it's going to really encourage you to solve this graphically. Now I'm going to do this one a little bit different. Rather than setting to 0 in example 3, I'm going to set this where I have the left side. So in equation 1, I'm going to enter square root x minus 5, subtract square root 2x plus 7. Equation 2, I'm going to enter in y equals negative 3. It will give me the same solutions, like the answers that I do it this way will be the same thing as what I did in example 2, but I'm actually chasing something different this time. I'm not going to find zeros, I'm going to find intersections. I want to know when these two graphs cross. So if you use the intersection method, left side, right side, make sure you don't find zeros, because that's the wrong answers. Make sure you find intersections. You set to 0, use 0 feature. Left side, right side, use the intersect feature. So let me show you how you do that on your calculator. Bring the calculator up again. Clear our equation. clear our key history. So what we're going to do in equation 1 is enter second function square root x minus 5, subtract second function square root 2x plus 7. So that's equation 1. And equation 2 is negative 3. So we're going to look for where these graphs cross, and that is going to be the solution. So we may have to adjust our window settings, but let's check it out first and see if we can see where these graphs cross. It looks like the graph was starting at the bottom left or bottom right corner, and then I could see my horizontal line, y equals negative 3. So I want to get a better picture of this. So I'm going to get rid of all that dead space in the top and left, and I'm going to adjust my windows. I'm going to start at x equals 0 and go to, say, 25 and go up by 5s. I'm going to go from negative 10 to 0 because I only need to care about when I cross 3, so I should get a much bigger picture. And in fact, I'm going to even adjust this a little bit more because it's still quite hard to see. I got a lot of space down at the bottom. Rather than starting at negative 10, maybe I'll start at negative 5 to 0. So I'll go from 0 to 25 on x. I'll go from negative 5 to 0 on y. And then I can see this graph a little bit clearer now. And again, even if you wanted to make this even bigger, you could do so. But we could go and find these points of intersection as well. In fact, I am going to zoom in on this a little bit more. I'm going to go from negative 5 to negative 1. And I'm going to go to negative 2. And see if that makes this a little bit easier to see. Yeah, maybe I can see that this thing does cross twice now, a little bit more clearly. And now I'm going to go find my points of intersection. You do this a little bit differently. When you find intersection, remember you're not looking for zeros. When you find intersection, it's still the same location. Second function trace to bring up the calculate menu, but choose option 5. This is actually an easier option to use because you don't need to set left and right boundaries. All you got to do is just make sure you are selecting the two graphs. I'm selecting equation 1, the square root graph, enter. I'm selecting equation 2, which was our horizontal line, hit enter. At guess, hit enter again, and it tells us our first intersection point was where x equals 9. That's our first answer. Let's try this again. Second function trace, 5 for intersect, but this time move our cursor a little closer to the other point of intersection because the calculator always defaults to the one on the left. Then go enter, second curve, enter, guess, enter, and it looks like we also cross at x equals 21. So there's two solutions to this question. X equals 9 and x equals 21. Now the moral of the story here with this type of intersect feature is even though it's a little easier to punch in because you don't have to set boundaries, you generally have to work with your window settings a little bit more using this method. So students that tend to find window settings and setting windows quite easy tend to like to use the intersect feature. Students that don't like to mess around with window settings as much tend to like to use the zero feature. My suggestion, try to get comfortable with both so that when you see questions that you can't get one way, try the other. It's really important that you know how to solve graphically. It'll save your bacon in a lot of questions. Alright, so let's write down our two solutions. X equals 9 and x equals 21. Should state our window settings. We went from x being from 0 to 25, and I think we went up by 5s if I remember. Y being from -5 to -2, and I think we went up by 1s if I remember correctly. Whenever you solve graphically, you should be stating window settings. You could have found this in your table of values as well. If you would have went scrolling through your table of values, because these are integers, it would have turned up in your table of values too. Let's do one more example. Example 4. Let's take this one, x squared minus 4 square root equal to 2x minus 10. And since the intersect method was the first time you saw it was in example 3, I'll do this one with intersection as well, just to keep practicing that second method. So y1, we're going to enter in x squared minus 4. y2, we're going to enter in 2x minus 10. And what we want to do is we want to determine the point of intersection. You could use this using the zero method, but you'd have to do a little bit of moving of terms all to one side, then graph the whole thing. This method, all we got to do is just enter left side, right side, find points of intersection. Now these answers are going to be the nearest tenth, so you wouldn't be able to use your table of values. You'll have to use, in this case, the intersect feature. So again, let's clear off the screen. Let's change our window settings back to our normal, so zoom 6. Let's clear our equations. And let's clear the key history. So I just start back from scratch. Equation 1, we're going to take the square root of x squared minus 4. Equation 2, we're going to enter in 2x minus 10. And you'll notice something a little bit strange about this. Because you're taking the square root of a quadratic function, you'll end up getting two parts to this graph, whereas taking square root of linear tend to give us a very similar shape. But these radicals can take on some different shapes depending on what you're taking the square root of. So let's just look at this in our standard window first. So we've got zoom 6, standard window. See if we can see a point of intersection. Our first graph are those two curvy parts. Our second graph is that line, straight line, 2x minus 10. Notice that the point of intersection seems to be up in our top right. I don't really care about the graph on the left because it looks like it'll never cross that straight line anyway. Graph on the left is going up and left. Graph on the bottom is going down and left. They would never cross. So we want to chase that point right at the top here in the right. So we're going to extend our x, we're going to extend our y using our window settings. So let's go from 0 to, again, 25, up by 5s. Let's go from 0 to 25, up by 5s, and we'll see how that looks. And again, I was just kind of guessing here. Notice that I was close to the point of intersection. So I'm just going to see if I can actually get it on my screen. Hit graph. And I guess I'm a good guesser because I see the point of intersection clearly on the screen. So let's go find it. Notice you will have to adjust window settings if you're going to use point of intersection. Use 0. You could use your standard window settings. So second function, trace, Option 5 for intersect. First curve is our square root function. Enter. Second curve is our linear function. Enter. Guess, hit enter again, and it tells us our point of intersection. We're supposed to give this answer to the nearest tenth, and there's only one answer. X equals 9.8 will be our solution. Let's close that off. X equals 9.8. Again, state your window settings. We went from 0 to 25 up by 5s. We went from 0 to 25 up by 5s. Now, while I won't be very picky about your window settings, when you get to a 30 pure class and you want to write a diploma exam, they will not mark the question right unless you provide window settings. So you're allowed to answer questions graphically, but you have to provide the solution, you have to provide how you did it, point of intersection or zeros, and you have to provide window settings so somebody can check your work using your window settings. So that's what we're doing in this lesson, basically graphing some radicals, stating some domain and range, and then practice solving using both methods. Solve using zeros, solve using points of intersection. I've done some zeros back in the last couple of lessons. This is the first time I'm introducing point of intersection, so I did 2 examples of that. In our next lesson on rationals, I'll continue using these 2 methods. Work on exercise 5.4. Take care, everyone.